Good morning, everyone. I am Mr. Ish. Thank you for joining me. An object that is released from a certain height or which is thrown from a certain height, the difference, the height being 1000 meters, acceleration being 9.8 meters per second square, assuming no air resistance, both of these objects will enter free fall. One object was merely dropped from a certain height, the other object was shot down from a certain height. You can see the difference in the initial velocities. This is zero, it was merely dropped. This was pushed down into free fall. What would be the time difference with regard to the impact of both of these objects? You know intuitively this will hit the ground earlier simply because it has a higher initial velocity. This has no initial velocity and it'll hit the ground afterwards. You would be surprised to know that the time differential between these two is minimal, and I will show that to be the case. We will focus on this case A first, which is an object that's merely dropped, versus case B, which is an object that's thrown into free fall. You have a certain height, you have a zero initial velocity, you have an acceleration. The equation you want to think about here is basically half at squared. In all instances, acceleration is equal to gravity, which is 9.8 meters per second square. We don't have to worry about the fact that the vectors are pointed downwards and you want to be using either negative or positive signs. Just keep everything positive because we're determining time. For an object that has initial velocity of 0, this is the equation you can do just to determine the time it takes to hit the ground. You know S here is equal to 1000. At the end I'll explain to you graphically why the differences are so minimal. You have acceleration times time square. But think about it. Acceleration over here is 9.8. You're being hit by 1.5. That's really just saying 4.9 t squared. You know this is an easy equation. You're just going to do 1000 divided by 4.9 and you'll do square root. You're solving for time. What will you get over here? Let's do it. You'll have 1000 divided by 4.9. You'll square root that. It'll take 14.28 seconds. And let's put that over here. 14.28 seconds. For an object that's dropped from a height of 1000 meters with zero initial velocity, having an acceleration constant of 9.8, it takes 14.28 seconds to hit the ground. Now let's focus on this. The interesting part over here is that initial velocity of an object thrown into free fall makes little difference, but we will mathematically show that. For this equation over here, you want to use nothing other than this equation right here. For this case, you want to use this equation. Initial velocity times time is equal to half at squared. Why are we using this equation versus the previous equation, which is just this? Because we have an initial velocity component, therefore you must incorporate that into your calculation. Plug in the items you know. You know the height over here is 1000 meters. You know initial velocity here is 10. You know time has to be determined. You have half a. Half times 9.8 is a 4.9 t squared. Bring everything onto one side. You have 4.9 t squared plus 10t minus 1000 is equal to 0. What do you have here? A quadratic equation. You have a, b, c. You run it through the quadratic formula. I'll just put the items out. You have minus b plus minus b squared, which is 100, minus 4 times 4.9 times minus 1000. This is your minus 4ac divided by 2a. 2 times 4.9. You're not going to look at the negative value because time cannot be negative. All of this is equal to time. You must focus only on the positive value. This item here combined with that item here with the plus and then divide by that. Don't look at that negative value. So you'll have 4 times 4.9 times 1000. You know all of this is a positive. Minus minus becomes positive, plus that 100. Square root it. I'm going to add it to minus 10. Minus 10 divided by 2 divided by 4.9. I have a time here of 13.3 seconds. The time here is 13.3 seconds. Granted, it's not much of a difference. Of course, as your height increases, the time difference will increase, but the time difference will never increase as much as one would think. Shooting an object into free fall or releasing an object in free fall does not lead to much change with regards to the time difference between the two cases. For the following reason, allow me to show it to you in terms of a graph. You want to think about everything here with regards to constant or uniform acceleration. What does that mean? Think about it. In both instances, whether you release or you throw an object, the acceleration is still 9.8. It's still a linear acceleration, which means at any given time interval, it's never changing. It's not an exponential factor, it's a linear factor. Graphically, all of that can make quite a bit of sense based on what I'll show you. On the x-axis, you always want to bring in your time. On the y-axis, you want to bring in velocity. But since we're looking at three different types of items here, we're looking at a position, You know height is position. You can think of that roughly as distance. We're talking about time, we're talking about velocity. You want to talk about velocity, time, and position and time, but the velocity and the position can share the same axis, your y-axis. If here's your 0, your position here is 1000. On that same axis, we can put the height, 1000 meters. We can also put here velocity. Imagine I have the velocity component here and the position component on the y-axis. Let's look at case A in terms of the velocity time graph. At time 0, initial velocity 0, you're going to shoot up like this in a normal linear manner because acceleration is always constant. The slope of velocity and time is acceleration. And then on the same graph, you're going to release an object from a height of 1000 and it'll go back down to its resting position at 0 when it hits the ground, and it'll come like right over here. That's your case A. Now what about case B? Case A and case B are no different. Their slopes are the same. The slope of a velocity time graph is your acceleration. In both cases, acceleration is the same, so you have two parallel lines. The case B graph is parallel to case A in terms of the velocity time graph, except it's just starting from a little higher height, 10 meters per second, and it's going to shoot up in the same manner. It's a linear line. Both A and B cases are linear line. And with regards to the position time graph for case B, you can have a situation which will be something like this, because it's going to hit the ground a little earlier. If you look at the intersection, now you'll see the difference in terms of the time is not much. You can look at right over here, from here to here, or from right here to right over here, and you'll see the time difference is not much. This is a difference in the time between the velocity and the time graph components. But if you want to look at from the position and the time, you can look at something like this. Again, the instances or the differentials are minimal at best. You'll see very clearly if an object is just merely dropped or it's thrown into free fall on a planet where acceleration is a linear factor, you won't see much difference with regards to the time differential. If, however, you were on a planet where acceleration is not linear, it's constantly changing based on the time intervals, then you can have exponential curves, and then the time difference will be huge based on an object thrown or released into free fall. But on planet Earth, acceleration is linear. These lines will always be linear over here. Thank you for watching. Have a good day.